at the CFCA, who have been working on telephony fraud for a little while with Merve on myself. I am a professor at EURECOM, so I have been here for a little while, and I'm working in general in computer security, and have this interest in telephony fraud. And I also work also on topics like embedded system security and software security more generally. And Merve Sahin is working with me on this topic, and we have been collaborating for a number of years. She's now a researcher at SAP, and she's working on telephony frauds and honeypots there. SAP, which has the research labs in Mougins, near EURECOM, which is in the south of France, on the French Riviera, who are just between Cannes and Nice cities. So we have been working on telephony fraud for a number of years, and of course we've heard about and seen a lot about publications from the CFCA, the studies and so on. So it's really a great honor for us to present our work here. So today we're going to talk about international revenue share fraud, IRSF, and in fact, we look really at IRSF as the way to obtain a monetary benefit from international fraud calls. Often in fraud, people use different terms for different things, and as we are academics, we tend to try to be careful about the terms and the organization. So we made previously a paper which we call the SOC, a systematization of knowledge, where we try to classify and map the different fraud mechanisms that exist. And the IRSF is this mechanism that is used by fraudsters to generate money or get some cash back from generating calls. On these, therefore, need some call generation techniques to generate these IRSF calls. And I assume many of you are very familiar with lots of the slides I do in the introduction, but Woggery, or this callback scam, is very common, and it's been always a problem in many places in the world. And typically the users, they see some calls, they will call back maybe, and calling back an international destination, they will fall for the IRSF scam fraud revenue mechanism. Of course, there are different mechanisms for generating calls. On any mechanism actually which allows to generate calls with paying for them is a good way for IRSF revenue share. And it's been for a while very popular in Barcelona. Barcelona is very well known for when people get their phones stolen, the SIM cards get very quickly into some SIM box to generate a lot of calls, international calls. This has been running for quite some time. In other cases, it can also be actually PBX, phone servers being hacked, either by leaving voicemails or asking for callback, or hacking into the voicemail, or directly hacking into the PBX. And there have been PBX typically have quite access to a big telephony capacity, so it can be a very attractive target to generate call for IRSF. So I imagine you're all familiar with IRSF, but I also take this opportunity to get feedback on our view of IRSF, if we miss things. And basically, we classify 3 actors in IRSF, right? We have an IRN provider who's going to provide so-called international premium rate numbers, IPRNs. The fraudsters who's going to obtain, probably I can point with my mouse. This, okay. No, sorry. So then the fraudsters, they will obtain the numbers from the providers, right? The fraudsters will use any mechanism they have access to generate, to get phone lines to generate calls. And these calls will then be intercepted by a fraudulent transit operator, right? On this fraudulent transit operator, instead of terminating the calls at the destination operator, they will stop the calls and terminate them on an IVR, for example, and they will then collect the revenue from these calls without paying for the termination of the calls. Also, sometimes the fraudulent transit operator or destinations operator, they're the same. On the destination operator is actually giving this cashback on the phone numbers, on the phone calls, and this happens sometimes. Okay. So one of the main reasons for IRSF is that two main enablers for IRSF is both the least cost routing policy, or even if that's a very big simplification, I'm happy to hear about you on this. Essentially, the idea that a customer will pay some amount and then an operator will have multiple possible routes, on some cheaper and some more expensive. And sometimes going to the more expensive routes, we may actually get to the rail operator, but a fraudster who doesn't need to actually terminate the calls may actually advertise very low cost, and therefore be very attractive and attract some traffic that will not be terminated, but instead will be kept. The idea is that one of the main difficulty is that there is lack of visibility on the telephony network. So someone has maybe someone should cut his microphone. I hear a dog barking on the back. Okay, so the fact that this opacity is making it quite difficult to address IRSF. Because we cannot easily know where the calls will go, right? And this is the main difficulty, and that's really in a sharp contrast with the internet, where we can do trace route or things like this, or know exactly where the calls are going. So we actually looked at these international premium rate numbers provider websites. These websites are typically publicly available. They will advertise ways to generate to get revenue from call traffic generation, etc. They will advertise some pay rates, how much they will pay for calls terminated to that or this number, etc. And we even see here example of payment sheets with the terms of payment, the delays, etc. On these websites are really public on the internet, right? And anyone can actually go see them. And they are advertising also on social networks. So we see on social network, for example, advertisement for fast payment of people who will generate traffic to these websites. The thing is, they also advertise the public test interfaces where people can actually go and try to see if they could generate money, generate revenue from these calls. And we can actually, what's interesting is we can actually go to this web page and see what are the successful tests, the tests that are the success, the tests that were actually received by this provider. And then see which calls can actually generate money. We also have to distinguish that when we look at these, we actually need to differentiate between test numbers and the fraud. Most of the time, the numbers we see for tests are not those which are actually used for fraud. The fraudster may need to try multiple numbers because some route will be stopped, some route will be blocked, some route will be unreachable, and so on. Or some route will not go through the hijack by the fraudulent operator. And therefore, a fraudster will need to try multiple destinations. When he gets a successful hit on these numbers, then he's going to usually have a dedicated interface and is going to be able to generate a lot of traffic to make a revenue. Those test calls, they often are one number in a range of numbers which are hijacked. Right? On this range, when we see one number, we don't exactly know what is the actual range that is hijacked or that is possible to fraud. There is also a question that we wonder a lot: is there any legitimate international premium rate numbers? So yes, in fact, the ITU, they have a guideline for this, and there are international premium rate services which exist, but these are very specific on plus 979 code, international number prefix, and these are the only ones that are legitimate for generating cashback revenue, right? These are the international premium rate numbers. On any use of cashback mechanism on international calls is not legitimate, in fact, when we look at this. So even if a terminating operator is doing it by himself, it's against the rules of the ITU as least as we understand them. Okay, so now if we look at this, we look at this problem with multiple point of views. We started with having a small range of numbers. We had 10,000 numbers in an operator range in a small European country. And we actually set up a static server there for a little while and see what happens, try to monitor if we see any things strange. And we also automated and generated test calls with phones in different countries in Europe. And we actually observed test calls generated from Germany and Italy to those numbers which we were supposed to receive that were hijacked, right? And we could verify that some calls that we generate ourselves were hijacked and never ended up on our PBX. What's interesting there is that we also saw some other calls that arrived to this telephony honeypot, and that should not arrive there because, in fact, this range of numbers was advertised as a technical test telephony number range, and there was no one supposed to generate any call. So we assume that this range was actually advertised for IRSF at some point. So this was giving us real confidence that we could actually see this for real, and confidence in how the process is working. We then also collected data from these international premium rate number providers, and we scrolled websites, the publicly available websites, on the websites with publicly available test numbers, test credentials for accessing these websites. And so we could actually collect information from these premium rate service providers, which I'll talk a bit more after. And we also were provided with some data sets with a number of calls from a victim operator, knowing there was some fraud case there, on which we evaluated. So if we look at this ecosystem of the IPRN providers, we identified 45 such websites, and for 12 of them, we actually made crawler to collect information from these test interfaces on test login credentials, the credentials which were publicly advertised on social networks or things like this, which were meant to be accessed. So we didn't break into any websites. So we did this data collection from January 2016 to November 2019. And we collected 3 million, more than 3 million distinct test IPRNs, and also several hundred thousands of test call logs, because these interfaces, they will also display the previously successful test calls. that were generated on this test code. So we actually know some of these test codes which were successful. If we look at the data set we got, we see that the IPRN cover 238 countries and territories out of 247. So it's really every destination is possible, on more than 1,000 mobile operators. So of course we see a higher ratio of advertised test IPRN on countries like Latvia, Iraq, and Cuba, which are usual suspects. And the origins of the test calls are very often from US, India, or Germany. This is again inside our data set, so it has its own meaning. It doesn't mean it's only a partial view, of course, of the problem. If we look at we try to get a sense of this data by trying to understand if the providers, let's say the fraudulent telecom operators, they provide these to a lot of different website data providers, or if they are more disconnected. And we saw that only 3% of all the numbers which were advertised were advertised by more than one provider, right? So, however, so basically the test numbers are quite specific to the providers. However, when we look at the last 4 digits, if we look at blocks of 10,000 numbers, meaning that we put a wildcard on the 4 last digits, we see that 80% of the numbers range are shared. So they all have all the test numbers providers have a different test number, but they seem to all fall into the same buckets in a way, right? And that the operators that hijack the number ranges are going to define different portions of the IPRNs to different providers. This is what we can see on this figure here, that if we have if we look at the numbers by removing the last 4 digits, they all have the same ranges, more or less. We also see that if we look over time, we see that the test numbers that are advertised are actually rotated in a way, right? Some test numbers will be used at some point in time and then stop, and then advertised later on, and then not advertised for some time, and then advertised again, etc. Or there is some rotation of these numbers, supposedly because these test numbers get stopped, blocked at some point, and then they wait a few months for the test numbers to be forgotten. Another thing that we looked at is how these test numbers actually spread in the country number space, right? So if we look at so on these figures, we plot actually the whole Latvia number space, okay, by putting the most significant digits here or the least significant digits here, and then we plot the numbers that we see in the data sets. And we plot in a different color depending on if these numbers belong to a different kind of range, right? So we see that we have a lot of IRSF calls that target Latvia on the mobile range, right? Some on the fixed, some on premium too. But we also see that there is a significant number of calls which are targeting unallocated space, right? So they are going to call the IPRNs that are advertised on numbers which cannot be terminated, right? Because there are no customers behind, so they can only be fraudulent. And this is, we think, a way as well to block, detect and block IRSF. We also can see better on CUBA, for example. On CUBA, we see that let's say the spreadness of the calls in the country are quite spread, right? In Latvia, it's more focused on valid ranges. In Cuba, it's a lot less. We can also see more clearly than we see on Latvia side that we have kind of lines, more dense lines, around 4-digit number range boundaries, right? So likely, we can observe this, and we explain it by quite likely the test numbers which are provided for test calls, not for the actual fraud, but for test calls that we see. They are provided at the beginning of the range, right? Therefore, we'll often, if we look only at these numbers this way, we'll only say, okay, this number is going to be used for fraud, for blocking, we block that number, but in fact, the actual fraud numbers, they will be later in the range. It could be. So, very common naive approach to block IRSF is to looking at the test calls, test IPRNs, sorry, on the number range. And it's kind of, there are two problems, right? If we block the whole range, it's going to be the risk of blocking legitimate calls. And then if we may make the range too big or too small, and if we block only the actual numbers used for the actual advertised IPRN, we may miss the actual the numbers that are actually used for fraud. Right? So there is no real very easy solution there. So we choose to we made in this study, we really thought we also observed that depending on the country, for example, the kind of patterns would be very different. So for example, in Latvia, the numbers are very concentrated in some areas, while in Cuba they are not. Right? So we cannot block with the same range in different countries, because they will have different habits or different number range which are hijacked. So our idea is to leverage on this knowledge of the IPRN providers numbers, on the domain knowledge, to engineer some machine learning features. We created 11 features, which means we basically compared the distance between test IPRNs. We looked at if that test IPRN is valid in a numbering database. We looked at if this country has a lot of IPRN advertised or not, or things like this. There are also some features that are based on historical call records. So we can compare the time to the previous call from the source number. We can compare the call frequency and so on. And then when we can run this on the numbers we collect from the IPRN providers, but also on the numbers that on which we want to detect the fraud, right? So the call logs from the operator. So we made a first evaluation on data set with a bit less than 700,000 calls from a small European operator. This is more or less 3 months of attention call for 6,000 users. And we use that to evaluate the effectiveness of this machine learning feature. So the first challenge we had with this is that we don't have I think in telephony fraud, we never have the ground truth, which means the truth, whether this is a fraud, this is not a fraud. There is always such a gray area, things that miss and go below the radar and so on, that there is never a real ground truth. In that case, we actually use 12 calls that hit some IPRNs to investigate, and after manual investigation, we actually identified 4 fraud cases from 4 different users, which lasted a number of hours or days, on collectively like 3,000 calls, fraudulent calls. Then we have a second problem, which is more like a machine learning thing. When we do a machine learning, typically you want the algorithm work better if you have a half good, half bad, and then you want to tell them apart. Right? If you train something with a very unbalanced data set, meaning that you have, in this case, where you have 0.0046% of calls, or that's 0.4% of fraudulent calls, then the data set is very unbalanced, and the learning is going to be very inefficient. It doesn't work well. So typical technique for this is to do some downsampling. So we're going to take 3,000 fraudulent calls on 3,000 benign calls, what we think are benign calls. And then we're going to do the learning on this only 6,000 calls with half good, half bad. With this, we use a random forest classifier, or we then train a random forest model for doing this detector detection mechanism. Now we could use this, and we basically compared to the naive approach, right? So naive approach being we're going to take all the calls, and we're going to identify which ones have hit a test call number, and then if there is a test call number, then we're going to take all the range of 100 numbers or 10,000 numbers, and this is going to be our baseline simple approach that we use to compare to. Then our method, something I didn't really explain, is we do a tenfold cross validation, meaning we take this data set, and then we're going to always learn to the training on 90% of it, and then we do the evaluation of 10% of the data set left, and so on and so on. And we do it with all the 10 different slices of the data set. And this allows to have a good understanding of the capacity of the machine learning technique to work. In the end, we obtain very good results. So essentially, we get to 96% true positive on less than 1% of false positive rate. Obviously, this is the most problematic is the false positive rate, meaning like blocking calls which shouldn't be blocked. It's pretty low, so that seems good, but I mean, depends. I'm not sure what's the point of view on operator on this. So if we compare to the naive approach with our technique, we have a 33% higher true positive rate, a slight increase of false positive rate. So overall, I think these results are pretty good. An interesting thing that we evaluated is that if we we said we have 4 cases, and they are slightly different. One is likely a SIM theft, and 3 are PBX hacking. If we look at doing the learning with excluding one of the PBX hack, we see that we can detect 100% of true positive. So we detect all the cases, meaning if we have some PBX hack in the learning, then we are very good at detecting the PBX hack. On the other hand, if we have only PBX hack in the dataset and we don't do the learning with the SIM, and then testing on SIM, we have 57% true positive rate. So the quality of the machine learning engine is going to be very sensitive to the quality of the data you have as input. To conclude, I want to give another evaluation on ongoing small experiments. Is that we actually use real-world CDR with this time ground truth from a fraud expert. And we had 2 months of data, and I don't have the total. I don't have the total size of the data set, but it's hundreds of millions of calls, I think. And we actually have 10,000 IRSF calls, which were manually labeled. First with detected with rule-based detection method, but then manually labeled. And we then use the machine learning method like said before, and then we obtain a true positive rate of 98%, which means that we detect 98% of the fraud, and we have only 2% of false positives, meaning calls we say are fraud but are not. This is pretty good. This is a preliminary result, and I think this is unpublished or no, but I think this can really be improved on. Although our work is research, it's, these are prototypes. There is a lot of work to be done to make this scale to real-world operator loads. But with this data, we can already have a fairly good idea that this approach could work on a real operator on a real time, right? With the learning being done, let's say, every day, updated every day, but then the detection done in real time. probably requires improvement of the code. We probably need to improve and optimize a lot. We probably need a good server for this with a lot of cores or something like this, but I think it's feasible. Further, we currently only use random forest. Using neural networks is also an option and is typically known for being better at detecting, being more broad at detecting events which are a bit different from what has been seen before. Okay, so with this, I just conclude by saying IRSF has been a problem for a long time. Apparently a very lucrative fraud. I don't have first-hand data on this. It seems that really, I mean, we can confirm, I think it's something that was known, but we can confirm that almost all countries and operators are affected by this. But there is a way to, by monitoring IPRN providers, there is a way to actually improve this detection. I can also say that this data set that we collected is now being industrialized, and there is a company that is providing this as a service. Okay, so with this, I want to thank you all for your attention. I'm open for questions.